Red Bull's 2026 car is in serious trouble and no one saw this flaw coming. The new FIA hybrid rules just exposed a massive vulnerability in Red Bull's power unit, a flaw that threatens their entire championship campaign. Internal data now confirms repeated thermal overloads in critical battery zones, and fixing it could require redesigning systems that are already locked in by regulation. Subscribe now, because if Red Bull can't solve this in time, their 2026 season could be over before it even begins. The 2026 Formula One regulations mark a complete reset for engine architecture. With the FIA mandating a 50-50 split between electric and combustion power, teams must now deliver unprecedented hybrid performance under stricter thermal, weight, and efficiency constraints. While Red Bull aimed to set the pace with its new partnership with Ford, the shift from customer engine user to full constructor has exposed critical engineering vulnerabilities that have only come to light under full-scale testing. From the outset, Red Bull's strategy was aggressive: prioritize energy recovery, push deployment to the edge, and squeeze maximum aero efficiency from a tightly packaged power unit. Their new engine is compact, light, and designed for rapid energy cycling. On paper, it's exactly what the 2026 rules demand. But in real-world simulations, the hybrid system is generating more internal heat than the cooling architecture can handle, and that's triggering a chain reaction of thermal instability. Leaked data from internal dyno runs and long-stint simulations shows that Red Bull's MGUK and battery loop can't consistently sustain high energy flow across a full race distance. During phases of intense energy harvesting and deployment, especially on power circuits like Spa or Jeddah, temperatures spike beyond safe thresholds, forcing the system into self-protection mode. This throttles performance output automatically and reduces boost availability to the driver, essentially neutering one of the car's main advantages mid-race. This issue is compounded by the team's commitment to an ultra-compact rear end. To maintain aerodynamic superiority, Red Bull integrated their battery and inverter systems into a tightly confined space, leaving minimal room for thermal dissipation. In theory, this tight packaging reduces drag. But in practice, it traps heat. And once the battery reaches its critical limit, there's no margin left for natural cooling to stabilize the system, even under lift and coast driving. It gets worse. The flaw doesn't appear under short bursts or qualifying simulations. It only becomes apparent after sustained race pace, meaning it likely wasn't caught early in development. That's a problem because the FIA homologation window is closing fast. Any major redesigns to the battery structure, cooling layout, or rear packaging would require partial revalidation or special dispensation, both of which are difficult and politically risky this late in the process. Internally, Red Bull is said to be exploring a workaround using real-time energy management mapping, essentially software that limits hybrid deployment before heat spikes occur. But that solution sacrifices race performance to preserve reliability. It's a tactical compromise, not a structural fix. And as teams like Mercedes and Ferrari press forward with their own power units, the margin for error is vanishing quickly. One compromise can cascade into multiple strategy limitations across an entire season. This vulnerability strikes at the heart of Red Bull's 2026 ambition. They built their power unit to lead a new era, not to survive it. But now, with the FIA regulations forcing full electric integration and narrow thermal windows, the team must pivot. And in Formula One, adapting under pressure is brutal. Every choice now will define whether Red Bull enters 2026 as the leader, or as the first big casualty of the hybrid revolution. Internal sources close to Red Bull powertrains have confirmed a recurring issue that emerged only during full-duration simulation testing: inconsistent thermal saturation across the energy storage unit. This means the battery does not heat evenly, creating isolated hotspots that trigger conservative protection measures. These measures are hard-coded into the control system. Once triggered, the entire deployment logic reduces output, even if only a few cells exceed optimal temperature. This systemic response drastically cuts performance, especially during high deployment laps where overtaking power is essential. This issue stems from how Red Bull configured their energy harvesting architecture. The current design prioritizes maximum charge recovery under braking, a choice that gives a performance edge in qualifying laps and high-efficiency circuits. However, that same aggressiveness produces a steep thermal load curve during races. Essentially, the battery is absorbing energy faster than it can cool, especially when air density is low or the track layout offers little relief between braking and acceleration zones. That imbalance becomes catastrophic when compounded across multiple stints. What sets this flaw apart is how track-dependent it is. On cooler, flowing tracks like Barcelona, the system behaves normally. But at circuits like Mexico City, where altitude affects cooling efficiency, or Baku, where the recovery deployment cycle is punishing, Red Bull's system breaks down. This variability makes the issue even more dangerous because it's not easily predictable. That means even if Red Bull finishes a race cleanly one weekend, they may suffer power cutbacks the next with little warning or control. Complicating matters further is the battery's internal structure. Red Bull and Ford opted for a high-density, low-profile cell array to maintain aerodynamic efficiency. While this decision reduced weight and improved packaging, it also reduced surface area for cooling. In other words, the very thing that makes the unit efficient aerodynamically now works against it thermally. Engineers face a brutal trade-off: either increase cooling and compromise aero or manage temperatures through software and performance sacrifices. To mitigate the problem, Red Bull is reportedly experimenting with predictive cooling algorithms. These models use AI-driven telemetry analysis to anticipate heat spikes before they occur, adjusting deployment rates dynamically lap by lap. This could, in theory, buy them enough time to avoid thermal shutdowns, but early tests show that these adjustments dull the car's edge under race conditions. Instead of sharp, aggressive deployment out of corners, the power ramps are softened, making the car vulnerable in wheel-to-wheel battles. There are also attempts to develop modular battery insulation zones, heat shields that isolate high-risk cells from others to prevent thermal spread. However, this type of intervention introduces complexity and delays. Any change to internal battery structure must go through FIA revalidation, and with the homologation deadline approaching fast, Red Bull has limited windows to finalize, test, and legalize these changes without affecting the power unit's eligibility. Perhaps the most telling sign of urgency is the absence of public confidence. Unlike in previous years where Red Bull celebrated milestones, this time they've remained silent. There have been no comparative metrics shared, no PR about top speed, thermal efficiency, or recovery superiority. That silence, in a paddock obsessed with signaling strength, suggests that Red Bull is not ahead there in containment mode. And in a field as competitive as F1, silence speaks louder than words. Inside Red Bull powertrains, the engineering challenge is now at full red alert. Their lead thermal systems engineers have been tasked with remapping the battery's energy flow from the ground up. This isn't just a software update, it's a complete revision of how energy is harvested, stored, and released throughout the lap. Their goal is to flatten the battery's internal temperature curve without sacrificing deployment torque, a balancing act that very few teams have ever achieved under hybrid-era regulations. And all of this must be done while staying within the rigid packaging constraints already locked in for 2026. To address overheating at the source, Red Bull is trialing an advanced multi-stage deployment logic. Instead of sending energy through a single release profile, the system now cycles through 3 different discharge modes based on real-time thermal readings, driver input, and GPS-linked track models. In short, the car will now decide how hard to push the battery based on where it is and how hot it feels, even if the driver wants full power. It's a revolutionary idea, but it's also controversial. It introduces latency and unpredictability into driver control, 2 things top-level drivers do not appreciate. Parallel to that, Red Bull is testing a microchannel cooling redesign inside the battery casing. Borrowed from aerospace engineering, this concept involves embedding ultra-thin fluid channels between cell layers, allowing coolant to directly absorb thermal surges. While promising, this fix is physically delicate and time-consuming to manufacture. It also adds weight, a critical issue given the tight 2026 minimum weight rules. And even if the system works in isolation, integrating it with the car's existing cooling network may require rear-end structural compromises, something no top team wants to do at this stage. Another solution on the table is changing the inverter's heat spreader composition, switching from aluminum-based alloys to high-dissipation composites like graphene-enhanced ceramics. These materials can redirect heat laterally before it saturates the core system, buying the battery a few extra degrees of safety. But these materials are rare, expensive, and untested in race conditions at this scale. Any failure would be catastrophic, and Red Bull knows it can't afford a DNF caused by a rushed experimental part. Meanwhile, Red Bull's data science unit is refining real-time predictive thermal algorithms to give race engineers a warning window several corners ahead of potential overheating. This system isn't just about protecting the car, it's about enabling strategic decisions mid-race. For example, backing off hybrid deployment for 3 corners to ensure full boost is available for an overtaking zone. It's Formula 1 level chess, but playing it right requires perfect models, driver discipline, and zero margin for error. With the clock ticking, the most difficult decision may be whether to accept performance limitations rather than gamble on unproven fixes. Red Bull's leadership is reportedly split. Some believe the flaw can be masked with software. Others fear that without hardware changes, the car will always be running in safe mode, quick, but never fastest. This internal debate is now reaching the boardroom, with Ford executives closely monitoring every test report. The reputational risk of entering 2026 underpowered could affect far more than just race results. The engineering race Red Bull is now in is unlike anything they've faced before. In the V8 and early hybrid eras, they worked with known quantities. But now, with a brand new power unit, a shifting regulatory environment, and thermal behavior that changes circuit to circuit, they're developing on a knife's edge. Every fix has a cost, and every delay compounds the pressure. If they get it wrong, it's not just a design failure, it's a strategic collapse. If they get it right, it will be remembered as one of the greatest technical recoveries in Formula 1 history.